okay, with respect to AB terminals. Okay, we can find the Thevenin's equivalent with respect to AB terminals as well as BC terminals. So this particular problem you can try on your own. I'll give you the answer. But this particular problem, okay, we have already done. Okay, I think you remember the answer. What we got here is of VTH is equal to 4 volts and RTH. I gave you an expression for the RTH here with respect to AB terminals. Okay, what was that RTH? This is an open circuit. This is a short circuit replaced by. Then these two are in series. Of course, these three are in series, and that resultant is parallel to the 4 ohm, and that resultant is going to be what? In series with 1 ohm. Okay, so I think you get now 3 plus 2 plus 5, okay, parallel with 4, and the whole result is in series with 1. So this is already 5 plus 5, 3 plus 2, 5, 5 plus 5, 10, 10 parallel 4, okay, 10 into 4 by 10 plus 4 plus 1, and so on. I can give you direct the answer. Finally, after simplification, you get 27 by 7 ohm. This is what actually we did in the last session, and you can try with respect to BC terminals. It's an easy task for all of you. Okay, you can try this, but I give an answer for it. Okay, so the answer you please note down for BC terminals that you can try. The answer is VTH is equal to 15 volt and RTH is equal to, this is 45 by 14 ohm. Okay, so please note down this answer for with respect to BC terminals in the 9th question of our classroom workbook. Okay, our classroom workbook, 9th question. Understand all of you? So with respect to AB terminals, you already got that answer. Now note down that, and also note down the question number 10. Let's move. In Thevenin's theorem, most of the problems are coming. Okay. Generally, the networks are given in the exam. Okay, which consists of dependent sources most of the times. Dependent source problems are very, very important, and the procedure to calculate VTH and RTH, particularly RTH calculation, in case of dependent source, we have a special procedure. Okay, that I'll explain you. First, you please note down, and you also note down the question. I think you already have the classroom workbook with you. Okay. So let's move on to the question number 10. You already have this, and please note down this answer for question number 9, second question with respect to BC. This is the answer. Clear? Now, let's consider this problem. Let's consider this problem. So in this problem, is asking VTH and RTH values. Okay. How do you find VTH? Again, you have either mesh analysis or node analysis. Yes or no? To find voltage or current anywhere in the circuit. We had elaborate discussion on how to find or how to solve the network using mesh or node analysis. And it is easy to find, the number of nodes, minimum number of nodes required to solve the network. And this is a node you can take because these two are in series. There is no need to take a variable here. Yes or no? And single variable you can take. After finding this value, voltage, you can jump from this point to this point because he's asking VTH. VTH is nothing but what? Voltage between AB terminals. When the load is off, already load is thrown off. Open terminals, load is already thrown off, and you are expected to find the voltage between AB terminals. So one way is that with the normal procedure, you can find V here. You can take V here and find this V and jump from this point to this point, and then you can get the solution for that VTH. Or else I want to do something different here for the same network, because if I proceed with this, V is one variable, Vx is another variable. I'm sure that I'm going to get two equations. I need to go for two equations. So it may consume time. Okay. But if I do like this for a given situation, if I do like this, take this one is 0. Okay. 0 potential node. and take this one is Vx, or you call it Vth. What is this? Vth. Actually, Vx is equal to what? Now Vth. Yes or no? So if I take this is Vth, and when Vx is equal to Vth, this is also becoming what? 2 Vth, no doubt. And now let us convert this into a voltage source with a series resistor. Understand? Okay. If we convert voltage source with a series resistor, what will happen here? It comes like this. 6 into 10, 60 volts and 6 ohm. The 6 ohm is in series with what? 2 Vth. Yes or no? Therefore, when all elements are in series, there is no need to take any variable here. You can directly solve with Vth and the node variable and the dependent variable. Node variable and dependent variable both are same because Vx is equal to Vth. Now with a single equation you can solve it. Okay. So these are the ideas you must get, instantaneously by looking at the network. Or else you get all these things through practice. Definitely when you practice more and more number of problems, you automatically get the ideas how to solve the network. Understand all of you? Okay. Well, this is all only to save the time I'm telling you. Otherwise you can go with the normal procedure. You will get anyway the answer. So here Vth and by 2 Vth plus 2 Vth minus 60 by 6. Yes or no? Okay. So Vth by 2, Vth by 2, Vth plus 2 Vth. Okay. What else here? Minus 60 by, this is what the resistor, right? 6 ohm is equal to 0. Or else I can directly write using inspection Vth of, using inspection, I hope all of you remember inspection method, 1 by 2 plus 1 by 6 is equal to touching negative minus 2 Vth, touching positive here plus 60 by, what is the resistance value? 6 ohm. You can take. Finally, you get the value of Vth here. Understand all of you? Okay. This is how we can calculate Vth value. So I can give you the answer here. It is 10 volts. You are supposed to get 10 volts answer here. Please, you can calculate it. You can cross check the value. Now, let us proceed with RTH calculation. All of you carefully observe here. Don't write. I'll give you sufficient time. Okay. I'll give you sufficient time. Then only you can note down. First, you look at this procedure and all. RTH calculation. What is the procedure to calculate RTH? What is the procedure? What is the RTH definition? It is a resistance determined across the terminals where the load is removed with all independent energy sources suppressed. Yes, sir. So if you suppress the independent energy source, this is replaced by open circuit. And now you are going to calculate the resistance between AB terminals seeing through the network like this. But what is happening? There is a presence of what? The dependent source. Okay, you cannot suppress the dependent source because this dependent source is depending upon Vx only. It will be suppressed only when Vx value is 0. Dependent source is depending on Vx, but Vx is not depending upon dependent source. Hope you understand the point. That is why when there is a dependent source, it is not possible to calculate because there is a source now in the network. You cannot now apply series parallel combination to determine RTH calculation. What we have done in the earlier examples. Yes or no? In the previous example, we calculated simply series parallel combination because there was no dependent source. But when there is a dependent source, you cannot really solve using reduction technique because there is a dependent source. Understand? Because you cannot really suppress that dependent source here. That is why in case of dependent source problems, there are two important methods. Based upon the situation, any one of those methods can be applied to determine RTH calculation. And I'm telling you this procedure will help you not only here, everywhere in magnetic coupled circuits, in two-port networks, in transient analysis, in AC circuits, wherever it is not possible to find the equivalent resistance using normal reduction technique, wherever normal reduction technique is not feasible in a particular given condition, there you are supposed to use the methods which I am going to explain. Understand all of you? Okay. So let us see what are those methods. So let us see RTH calculation, right? Let me put the heading methods to determine RTH in case of dependent source problems. Not only dependent source problems, I am just giving a general title here, but I am telling you methods to determine RTH or methods to determine resistance, equivalent resistance across any two terminals where normal reduction is not possible. So same procedure is applicable to that also. Understand? Okay, but I am giving a title because we are in the context of RTH calculation in the theorem. So therefore I put a title here. But you can generalize the same procedure to everywhere, wherever it is not possible to determine the equivalent resistance using the normal reduction technique like series parallel. Understand all of you? Okay. So now let us see method 1. What is the method 1? It is simple that we learned Thevenin's equivalent resistance is nothing but open circuit voltage by short circuit current. That is nothing but Thevenin's equivalent voltage by Norton's equivalent current. You can use the formula, but sometimes the formula may not be feasible. Understand all of you? Okay. Sometimes the formula may not be convenient to apply for a given problem. I will also give some examples in that while doing the problems. Okay. But initially we will apply two methods. Okay. And we'll try to learn how we can apply. And then later we will understand in a particular context which method is the best method to apply. Okay. Method 2. This is method 1. Method 2, I told you already that some cases method 1 may not work. Okay. Now here method 2 is nothing but volt amp method. Volt amp method. But to apply volt amp method, certainly, all independent energy sources must be suppressed. All independent energy sources, energy sources must be suppressed or deactivated. Suppressed or deactivated. Understand? Okay. What do you mean by deactivating the source? You already know. Replacing those energy sources by their internal resistances. Understand all of you? What will happen when you replace all independent energy sources by their internal resistance or deactivating the independent energy sources? The resulting network is assumed to be passive. Okay. The resulting network. Okay. Then the resulting network is assumed to be passive. We are not sure whether that resulting network is passive or active because there is a dependent source. I did not suppress the dependent source and I do not know what is the impact of the dependent source in the given network. Therefore, I cannot conclude whether it is really passive network or active network. But I still assume that. I can assume until I get the confirmation at the end of the solution, we can confirm. After finding RTH value, I can decide whether the given network is passive or active after suppressing all independent sources. Usually, when all independent sources are suppressed, when you do not have any dependent source in the given network, what is the network? What is the resulting network? Resulting network is obviously passive network. But now, in the presence of dependent source, this is a very important point. In the presence of dependent source, the resulting network, after suppressing all independent sources, may or may not be passive. We do not know about it, about the resulting network. But to proceed further, what is the assumption that we are making here? We are assuming that the resulting network is assumed to be passive. That's it. This is an assumption, Anna, only to proceed further. But we decide later after finding the value of RTH. Looking at the RTH value, we can say whether it is passive or active. I will let you know in the due course of time. Understand all of you, okay? Well, so Oldham method and formula, both formula and Oldham method, we are going to use it. According to Oldham method, okay, what do we do here? According to Oldham method, what we do here? Simple. It's like, you connect. This is what the network, right? And you are suppressing all independent sources. That means it is assumed to be passive. Okay. All independent energy sources are deactivated. Okay. That means this network is assumed to be passive. Now in Oldham method, you connect either a voltage source or current source, doesn't matter. Okay. You assume some voltage source is connected and also assume it is delivering some current I. You are injecting some current I into the network. Now you apply any simplification method that you know. Obviously either mesh analysis or node analysis most of the times. You apply any method which you feel comfortable for the given problem and find the relation between V and I. That means you calculate V is equal to something into I. This something is obviously nothing but what V is equal to IR, and you are finding the resistance across the terminals where the load is removed, right? With all independent sources suppressed, you have a name for it that is nothing but RTH, because the definition of RTH is what? Remove the load, find the resistance across the terminals with all independent sources suppressed. There is a special name for it, otherwise it's simply equivalent resistance, but because you are removing the load and suppressing all independent sources, you are calling that resistance as RTH. Clear all of you? Okay. Some people use current source I and assume there is a voltage V. They inject the current by using a current source I and they take voltage across it. It's something like this. Different textbooks follow different procedures, I'm telling you. This is I and this is V. Again, same thing, right? If you take now any node analysis or mesh analysis, any method that you feel comfortable, you get the relation between V and I again. Finally, the volt amp relation between, okay, the across AB terminals, if you are able to find, you can express V is equal to something into I. That something is nothing but RTH value. So either you can use current source or voltage source. If you use the current source, the voltage is V. And if you use voltage source, then you can say that it is delivering some current I. That's it. But finally, you want relation what V is equal to something into I. In some textbooks or some, procedures are given in different materials or textbooks, let us say. Sometimes they assume that V is equal to 1 volt. If they assume V is equal to 1 volt and proceed, they get some current. Yes or no? Now what is the resistance? Actually the formula V by I. Voltage is what? 1. Current is how much? I, you are getting that value you are finding. Here you are assuming with 1 volt and you are getting the value of I here. Okay. Now what is the resistance? The ratio of voltage to current. Since you are opening the load and finding the resistance, therefore you are calling RTH. So reciprocal of that current value is nothing but RTH. You understand all of you? Okay. Some people assume I is equal to 1 ampere. I is equal to 1 ampere. And they find again the voltage value here. With this, okay, if I is equal to 1 ampere is taken, then you calculate V, right? Then again, what is resistance, Nana? Resistance between AB terminals, because you are removing the load, you call it RTH. Then again V by I. So I is assumed to be 1 ampere. So whatever the voltage value you get here, because its denominator is 1 ampere, 1. Therefore, whatever the value that you get here, voltage, okay, that is nothing but what? RTH value. So different people, different ways of calculation. Understand all of you, okay? Your wish, whether you take 1 volt or 1 ampere. If you take 1 ampere, then what is the corresponding voltage, and take the ratio. If you take 1 volt, then what is the corresponding current that you are getting, then take the ratio. Finally, you calculate R is equal to. Understand all of you, okay? So this is the procedure. So let me again summarize. How many methods are there? 2 methods. What is the first method? First method is RTH is equal to open circuit voltage by short circuit current. I can find comfortably what is the VOC and ISC. I know very well, right? So this is very simple and easiest method. Okay? But you need to calculate VOC, node analysis and apply, then calculate it. For ISC also, once again you have to solve from the beginning, applying node analysis. Then you have to find the ratio. No doubt sometimes it may take time. Okay. Now, the other method is what? Old-time technique. But to apply old-time technique, what is the important condition to be observed here? The network must be passive. Understand? Old-time method is applicable only to a passive network. Okay. Old-time method is applicable to only passive network. Now you need to convert the given network into passive. How do you convert a network into passive? You have to suppress the energy sources. Which energy sources can be suppressed? Only independent energy sources can be suppressed. Dependent source cannot be suppressed because we do not know the background of it. Because dependent source is a fictitious source, imaginary source. Okay, and dependent source is depending upon the dependent variable, either voltage or current. So you cannot suppress it. Therefore, what you do is, all independent sources must be deactivated or suppressed. First you suppress them. And the resulting network you assume it is passive. Then we will calculate RTH value. We will see based on the RTH value. If that RTH value, based upon that RTH value, we can decide whether it is an active network or passive network, that we can see. But initially, to start with the problem, we are assuming it what? A passive network. Understand all of you? This is very, very important, Nana. So first you please note down, I'll give you some time here. Quickly note down these points and then we proceed to solve this problem to find RTH value. Please. Method is going to help you a lot in the total journey of our network theory. We are going to use this method, Nana. Very, very important. Okay. Let us first apply the method 1. I think you have noted down all these things. Okay. Let us proceed with method 1. What is method 1? According to method 1, you require VOC and ISC. Just now we determined what is VTH value. How much you got? 10 volts, right? So let us find ISC also. Okay. According to method 1, we require VTH, VOC and ISC. Already we determined this. Let us try to find ISC value. What is the procedure to find ISC? Please draw the network again for ISC calculation, all of you. Okay. All of you calculate, all of you draw it again. Okay. I'm going to redraw the network. Please, all of you draw it. Draw it along with me. Don't waste time. Okay. You please draw it again. You can draw along with me. Right. So what we'll do here, you generally, to find ISC, what is the procedure? You short the terminals. And this is what ISC. Yes or no? Okay. What will happen when you short these terminals? Vx will become 0 because voltage across the short circuit is 0. So this is completely neglected. Once Vx is 0, this is also becoming 0. 2Vx will also become 0. And this is a voltage source, Nana. Voltage value 0. Voltage value 0 means what? Short circuit or open circuit? Voltage 0 refers to short circuit. So this is shorted. This is neglected. This is completely a short circuit. Now it is something like this. There is a resistor and there is a current source. Since voltage 0, it is behaving like a short. It is neglected because across the short, and finally this is a short. These are the AB terminals. Now what will happen? This 10 amperes directly flows through the short circuit. 6 ohm. It finds always a least resistance path when a number of elements are connected in parallel. 6 ohm and the short parallel. Yes or no? This 10 amperes is directly flowing through The short circuit ISC is equal to 10 ampere. That's it. Now, RTH calculation according to this formula VOC by ISC. Okay, VOC by ISC. What is VOC? 10 volts just now you got in the calculation, and 10 amperes you got. This is 1 ohm. Understand? This is method 1. Let us also see method 2. Let us also see method 2. Note down this. Meanwhile, I just erase that. Please note down this. Method 2. Quickly complete that. We will go with the method 2 here. Method 2. According to method 2, old-time technique or old-time method, we have to suppress all independent sources. Independent energy sources must be 0. That means they are suppressed or deactivated. Okay. That means current source must be replaced by open circuit. Yes or no? Let us do that. So what is the resulting network you are getting? The resulting network is like this, and it is assumed to be passive, Nana. Yes or no? We need to convert the given network into passive. We need to convert the given network into passive. 2 ohm plus or minus Vx. This is 2 Vx. 6 ohm. Okay. Now, you are going to connect a source. You are going to connect a source across the terminals where the resistance is required. Yes or no? According to method 2, what? You are connecting a source. Old-time technique says that you connect a voltage source or current source, whatever you wish. I generally connect a voltage source and assume some current is delivered I. I am injecting. This is what the whole network for which I need to find the resistance. For this, I am injecting some current with an assumption that there is a voltage source V. Now I need to obtain the relation between these two. I can proceed even with 1 volt and then corresponding current I can find, or else 1 ampere, then corresponding voltage I can be determined here. That's not a problem. Okay, but I'm taking V and I. That doesn't make any difference at all. Now let us see. We need to get the relation between V and I. Okay, what is V and I here relationship? If you take 0, can I assume this is V? Definite, not assume, but it will become V because there is a voltage source already connected. What is the voltage here? Definitely V. Now let us get V and I relationship here. Again, node analysis is the best method. What is the current here? I minus I. V by 2. V plus 2Vx by 6 ohm is equal to 0. First equation. Then you have another equation required because we need to eliminate Vx value, but you already know Vx is equal to what? V only. Substitute this Vx here and get the value of V is equal to something into I. You will get it. All of you simplify it quickly here. I'm sure that you will get RTH. This is nothing but what? RTH is nothing but 1 ohm you are supposed to get. Already we know the answer here. The same answer you are supposed to get. So this is the procedure to determine RTH using old-time technique. Simple. Suppress all independent sources. Remove the load. Connect the source. Either voltage source or current source, doesn't matter. I'm taking voltage source for my convenience here. Voltage V. Assume it is delivering some current I. Apply any well-known method. Usually node or mesh analysis only. Usually we go for node analysis most of the times because more comfortable. Right? So apply any method, known method. Get the relation between V and I. V is equal to something into I. Okay? That something is nothing but RTH. Do it. Both the methods and the same answers You got here, answer is same, 1 ohm and 1 ohm you are supposed to get. Most of the problems in Thevenin's theorem, Norton's theorem, maximum power transfer theorem, okay? And all these theorems, dependent source problems are coming very frequently. So you must be good at calculation. You must not do any calculation mistakes. Okay? Please note down that. Meanwhile, I just note another problem here. Eleventh problem in classroom workbook. Eleventh problem in the classroom workbook. Determine Thevenin's equivalent. What is the question? Determine Thevenin's equivalent. So most of the students, face the problem in dependent source cases. That's why I'm just trying to do as many problems as possible on dependent source cases. Okay? I'm just noting down the problem as it is given in the classroom workbook. Please all of you note down this once again in your notebook. Yeah, this is what given. 6 volt, 5 ohm, 1.5x, 3 ohm, 4 ohm. And this is what the dependent variable upon which dependent source is depending. And AB terminals are given open terminals. Now with respect to AB terminals, he is asking what is Thevenin's equivalent. Okay, all of you. Hope you're done with this, right? Let me take it off. Okay, so let us try to find now VTH and RTH. Our objective is to find VTH and RTH. Our objective is to find VTH and RTH. Now let's find VTH here. How many equations you will get here? Node analysis, I can go directly. This is V, and once you get V, then jump from this point to this point, you'll get VTH. Okay, right. So what is V? V of 1 by 5, 1 by 7, yes or no? Entering current 1.5 Ix plus, it is plus, because entering current outside I'm sending, it's an inspection technique, 6 by 5. Equation 1, because Ix is supposed to be eliminated. What is Ix here? V by 7. Second equation. Solving the two equations here, you will get V is equal to something and Ix is equal to something. Understand? Okay. What is V value? I give you directly the solution here. I get V value here, that is 9.333 volts. Please calculate it after solving 1 and 2. Substituting equation 2 in 1, you will get here Ix is equal to V by 7. 1.5 into V by 7, and again bring it back here, I mean to the left side. You can simplify it that easily, okay? So V is equal to 9.333 volts. Once you find V value, you know that these two elements are connected in series. Okay, how do you find VTH? Now V can be divided between these two because these two elements are connected in series. What is the total voltage available, Nana, here? V. Now let's divide because two series elements. So VTH is nothing but 4 by 4 plus 3 into V, and substitute here. You will get 5.333 volts. This is what actually you will get. Understand? Okay. VTH value you got 5.333 volts. Or else you can find Ix substituting here. Then that Ix into 4 is nothing but VTH. That is also calculation. Your wish. But finally the answer is what? 5.333 volts. Now according to method 1, first we look at method 1 because dependent source, RTH calculation using method 1. What is the method 1 formula? RTH is equal to VOC by ISC. But we need to find ISC. Okay, we need to find ISC here. Let me draw the network again here. Quickly. All of you please proceed. I think you have noted on that. Note on that all of you. I'm just drawing the network meanwhile. Please note on that quickly. 1.5 Ix. Now you are short circuiting these two terminals A, B. Okay, this is nothing but you are calling ISC or I Norton's 4 ohm, 3 ohm, Ix, 5 ohm, 6 volt. Understand? Now, this is neglected because short circuited. Yes or no? Now again take V of 1 by 5, 1 by 3 this time because this is gone. Yes or no? This is gone. There is only resistor left over. This is equal to 1.5 Ix plus 6 by 5. This is equation 1. Ix is equal to V by 3. Substituting equation 2 in equation 1, you will definitely get, because here I think Ix is nothing but what ISC, because this is neglected, the same current is flowing. So I think better we substitute V in terms of Ix, better I think. Yes or no? Or else if you substitute Ix is equal to V by 3, then you get directly the V value, then again you have to find Ix. Instead of that, substitute V is equal to 3 Ix in equation 1. Then you directly get Ix. Nothing but what? ISC. Because here very clear. Both Ix and I Norton's both are same because neglected. These are okay, the same path they are in. Now you calculate. You will get the value of. I just give you here the answer. Ix is nothing but 12 ampere. Understand? Okay. Now according to the formula, what is RTH now? Just now you have seen the formula. VOC is how much? 5.333 volt. I Norton is how much? 12. You will get 0.44. Okay, 4 ohm. Okay, you can calculate that. You will get 0.444 ohm. So this is how you need to calculate. So one must be good at solving the networks, particularly dependent source networks. If you are really good at solving the network, okay, you can easily find all this. So that's why I keep on telling always that one must be master in solving the network using node analysis or mesh analysis. Most of the times node analysis we use, but you must be good at all the methods. Okay, please note down. We'll go for second method. First, you please note on that. Now let's proceed with the second method, method 2. What is method 2, Nana? Method 2, Oldham. According to Oldham method, first you have to suppress all independent sources. independent energy sources must be 0. That means suppressed or deactivated. How can you deactivate here? Just look at this. I can replace it by short circuit. Yes or no? I can replace it by short circuit. And connect a source across the terminals where the resistance is required and inject some current I, let us say. This is what the whole network you have to find RTH. Volt-amp method according to suppress all independent sources for the resulting network. This is what the resulting network you keep in a box and then you inject some current using voltage source. Okay, now we need to simplify it. We need to get V in terms of I. Now what will happen if you simplify here? Now this is what the network, all of you please draw this again, okay? Again you draw. Again you draw. According to volt-amp technique. This is what the network arrangement you are supposed to make. You can see here. This is 0. This is definitely V. And there is one more voltage V1. Yes or no? Right? One more voltage. Now you get the equation something like this. Here if you write the equation, what do you get? Entering current I minus I, V by 4, V minus V1 by 3. Clear? Next. V1 minus V by 3. Here I am writing the equation. V1 minus V by 3 minus 1.5 Ix V1 by 5. Yes or no? Now how many unknown variables are there in the two equations you have? Anyway, V and I not a problem because you are expressing finally V in terms of I. But what are the other variables you have? One is a Ix, the other is a V1. We are supposed to eliminate them. So what is happening here? The simplification part is increasing. Okay, becoming more complex. To avoid the calculation or to reduce the time, you got an opportunity here to convert this current source with a parallel resistor. Can be converted to what? A voltage source with a series resistor. When you convert, all these elements will become in series, then V1 can be eliminated easily. Yes or no? V1 can be eliminated. There is no need to take V1 variable once you convert these into, okay? Yes or no? Okay, we'll do that. So once you convert that, how the network becomes here is something like this. Okay, what is this? 5 ohm. 1.5 into 5. 7.5 Ix volt. Okay. Now let us proceed easily that this is V. Now let me write minus I plus V by 4. V minus 7.5 Ix by, what is this? 7 is equal to 0. But I have Ix, that is another variable here. I need to work out. How do you find Ix here? It's nothing but current through this resistor. What is the voltage once you take this is 0? This is 7.5 Ix. 7.5 Ix minus V by 7 is nothing but Ix. That is one way. The other way is what? Ix and I both are flowing here. So I can write Ix plus I into 4 is also V. There are two different ways you can write. Okay. Anything is okay, but I'm writing this one. That Ix is nothing but 7.5 Ix. This is the voltage source value. Nana. This node is operating at what? 7.5 Ix volts. 7.5 Ix minus V by 7 is nothing but Ix. Second equation. Solving now 1 and 2. That means Ix you are substituting here. Okay, simplifying. You get V is equal to something into I. This something is nothing but you call it RTH. You are supposed to get 0.444 ohms. Already have solved the problem in the previous method. You already got 5.333 by 12, right? The same answer you are supposed to get. So what I'm trying to do here in the second equation, you are now expressing that Ix in terms of V, and you are substituting that Ix in this equation. When you substitute, this entire equation is turning into V in terms of I, or only in V and I. that now you rearrange or you express V in terms of I. That's it. Simple. You are going to get V is equal to something to I, nothing but the something is nothing but RTH is equal to 0.4440. Please do that. So I think you understand how we simplified this. We converted using what? Source transformation. Wherever there is an opportunity, don't miss it, because you can reduce the number of variables, and we discussed the point also in the source transformation. The source transformation can be exploited or utilized in reducing the number of equations, okay, when we apply node analysis. Okay, so please note down that quickly.